Welcome to video lecture E5. This one is on vectors, linear combinations, and span. So the objectives of this video lecture are to understand how to do basically arithmetic operations with vectors and to visualize what their geometrical meaning is in R2 and R3, to what we can visualize easily. In many situations, linear algebra, we want to work in higher dimensions, but understanding the dimensions that we can visualize is a very good first step to helping us figure out what's going on. So we'll want to be able to take sums, scalar multiples, and something called linear combination, which is rescaling vectors and then adding them together. And then we want to analyze whether a certain vector is in the span of a given set of vectors, which basically means can it be written as a linear combination of the given vectors. That will turn out to boil down to solving a system of linear equations, which has been the theme recently with all of these things. Okay, so here we go. So what's a vector? So you've probably seen vectors somewhere before. They represent things that are, instead of representing thing that just has, one particular value, if you need to have something that has multiple values all collected together, they come up all the time. If in physics you want to represent a force that has 2 or 3 dimensions, of course you need them. But you can also think of a vector that keeps track of all kinds of data about you personally, like your age, your annual income, whether you own a house or not. All of that kind of data can be collected and analyzed, and in fact is being done so every day now by various companies that want to market things to you. But abstractly, all a vector is in R to the n, it's just an n tuple of numbers. You just take a bunch of real numbers and you stick them all into a single object. And you got used to writing coordinates long ways, and often that's more convenient just for fitting things on the page. But often we'll write them as a one-column matrix like this, U1, U2 through UN. And we'll call that a column vector. And that represents points in the plane in a simple way. So for example, here's the vector 3, 1, 3, right? So x-axis it's 1, y-axis it's 3. So this red vector is 1, 3. And this vector is 2, 1. The green vector is 2, 1. Okay? So now what you can do with vectors is you can add 2 vectors, and you can just do it coordinate-wise. But that also has some geometric meaning. So if you want to add 2 vectors, what do? So for example, here I've got this red vector and this green vector. Well, if I can draw this right, I'll put the red vector at the tip of the green vector and draw something parallel to it. So that's meant to be the same direction as the green vector. Now I'll take the translate of the green vector and take it from the red vector over here. Okay, and what you see is that I've got this nice little parallelogram, right? Which might have some integer points in it, that's fine. So this vector here, which I guess I would draw separately. I lost my blue marker, so I'll use orange here. So going from the bottom here, from the origin, out to here, this is the sum. So that's what the parallelogram rule says, is that if I want to add the red vector to the green vector, then the sum is just the diagonal of this parallelogram. Okay? But that turns out to be the same thing if I think about adding it, just the numbers, right? If I take, let's see if I can do this right. If I take 3, 1, and I add to it 2, 1. Let's see, I guess actually this was 1, 3. So I'll fix that real fast. So if I take 1, 3, and I add it to 2, 1, then what I get is the orange vector here, which is, just add across. 1 plus 2 is 3, 3 plus 1 is 4. So this is the vector 3, 4. Okay, so that's that point in the plane. And you can think about these as being vectors from the origin, or you can just think about them as isolated points in the plane. Either point of view is okay. But one of the things that we'll want to think about is, we can do these, we can add vectors coordinate-wise, and you can also rescale them. You can multiply them by 2. So here's an example where I've taken this green vector and multiplying it by 2 just extends it to this next intersection point. Okay, and multiplying this by 2 extends that to its intersection point. Multiplying it by -1 reflects it and across the origin, and so sends it down there. Similarly, multiplying the green arrow by -1 sends it down there. Okay, so you can think about this line as just being the set of all multiples of the green vector, the one that's got the green arrow on it, and this other line is the one that's all the multiples of the red arrows. And then all the things you can get by adding any multiple of green to any multiple of red is, well, you can actually get any point in the plane, because if I'm allowed to use fractional multiples, I can get anywhere I want. The intersection points are just the lattice points, which are the points that I can get with integer coordinates, but that's not. Here I'm talking about k being, the things I'm allowed to rescale by are real numbers. So I actually get everything in the plane that way. Okay, so here are the algebraic properties of r to the n. So these are really going to turn into vector space axioms. So if you're a math major, you'll see these things come up later on as an axiomatization. You know, just like in Euclidean geometry, we have axioms that discuss the relationship between lines and triangles and things like that, and we build up from there. These are the basic properties that we build up from. They're so familiar from all your algebraic experience, I don't think they'll cause you any trouble, but we have to write them down here just so that we know that we can use them legitimately. And if you want to think about more abstract vector spaces, which will occur for many of you later on in your math careers, even if you're in engineering, then these are the properties that you can count on. And so what are they? Let's just go over them quickly. So the first property says that u plus v equals v plus w. And if you think about that parallelogram law, that should make a lot of sense. There's no order in which really one thing is added to another and it makes any difference. This one looks kind of mysterious. It's called the associative property. And it says that if I want to add 3 things, well, I can add the first 2 together and then add the third one to it, or I can add the last 2 together and then add the first one to that sum, and I'll get the same thing. So perfectly standard and believable. There's a 0 vector that you can add to, and there should have been a hat on top of that, 0, 2, sorry. So if you add the 0 vector to anything, it just stays the same. It doesn't change anything. And finally, we've got a negative of something. So if we take a vector and we add its negative, then we get 0. And it doesn't matter, again, it doesn't matter which order we add those 2 things in. So those are all axioms that involve just the addition part, the additive part of the vector space. Now over here, if we're going to do scalar multiplication, well, we've got a distributive property, right? We can scalar multiply times the sum of 2 vectors. We can either add first and then multiply, or multiply each one first and then add. And you might want to go back and look at that graph, that sort of grid I just drew, and think about how that should make sense in that context, right? Now here, if I've got c plus d, I can add 2 scalars together and multiply times the vector. So I can make a vector longer by c plus d by just adding, take how much longer it is by c, then extend it by that much more by d. And so that's what that one's saying. Here, if I want to multiply by 2 scalars, I can either multiply the scalars together and then multiply times the vector, or I can multiply them one at a time times the vector. And this says that I've got an identity scalar that I multiply times u, and I always get the same thing back. Okay? Notice that there's no axiom that involves multiplying 2 vectors. So there's no way to take 2 vectors and multiply them together and get another vector. I mean, yes, there's the cross product. That turns out to be a very special case for R3 and is not something that works even for our other values of r to the 4, r to the 5. All of these things work in any dimension, and they work much more generally. So there's no way to multiply 2 vectors and get another vector. Later on, towards the end of the course, we'll see a way where we can take 2 vectors and do an inner product, which gives us out a scalar. So that'll be very useful, and that'll help us determine the geometry of our systems, but that's not for now. So for now, we're just dealing with adding vectors together and rescaling them by scalars. So you always have to have a set of scalars. Here, for us, it's just the real numbers, but you could be dealing with the complex numbers just as easily, and maybe you need those for some applications. Okay, So those are the vector space axioms, and that's what's going on. So now, here's an important definition, the linear combination of vectors. So if I've got a bunch of scalars, which I'll call C1 through Cp, then I'll call a vector y, which I can write as C1 times V1 plus C2 times V2 plus Cp times Vp, a linear combination of those vectors V1 through Vp. Now the book, this is a notational issue, the book just writes the V's in boldface, but the boldface V's don't look very different from the regular V's in the videos, at least with the kinds of fonts and things I'm using. So I'm going to write the arrows above it just to make very clear that the distinction between vectors and scalars. And if I mess it up like I did with that 0 on the earlier slide, you should feel free to point it out to me and I'll fix it in case I ever redo these videos. Right, so thinking about linear combinations, let's go back and take a look at this picture again. So over here in this picture, what's going on? Well, if I wanted to, I could suppose I wanted to take 2 times the green video. Okay, so 2 times the green video would mean take that arrow. And now suppose I wanted to add it to the negative of the red video, the red vector, sorry. So there's the negative of the red vector, and there's 2 times this. And if I add those guys together, well, you can see the parallelogram rule, right, is saying that I guess that this should just go down to here. So this vector is the linear combination, which is, let's see, which one of these? I guess I'll call the green one V1. So this is 2 times V1 minus V2. So that's an example of a linear combination. And in fact, all the intersection points here are the integral linear combinations, the integer linear combinations of these 2 vectors, and the points in the middle are the ones that I get by taking fractional linear combinations. So for example, if I took, for example, this vector here is 1/2 V1 plus 1/2 V2, right? That one right in the middle. Okay? So that's what a linear combination looks like geometrically, and in higher dimensions you could end up with, you can imagine these kinds of grids filling out 3-dimensional space if you like. Okay. So now that we've seen what a linear combination is, let's think about what, it's easy to write a linear combination of some vectors. If I give you some vectors and some scalars, you can create the linear combination, why, no problem. But the question is, can we go backwards? This is often true in mathematics that, it's easy to go one direction and hard to do the inverse. So in particular here, you can ask the question, suppose I say, I'm going to give you y, and I'm going to start off with y in some set of vectors and say, is there a way to write y as a linear combination of those vectors for some scalar ci? Okay, so let's take a look immediately at an example here and see what we can do. So the first thing to note is, what does it mean to write it as a linear combination, right? If I'm writing something as a linear combination, then really what I'm doing is I'm saying that I want to find values C1 times 1, 2, minus 1, plus C2 times 2, 4, minus 2, plus C3 times minus 1, 3, and that should be equal to my y minus 1, 4, 5, which is equal to y. And so if you think about that again, what you're really saying is, okay, well, I need c1 times 1 plus 2 times c2 plus negative 1 times c3 to be negative 1. Right? This is equivalent to saying, okay, c1 plus 2c2 minus c3 equals negative 1, 2c1 plus 4c2 minus c3 equals 4, and negative c1 minus 2c2 plus 3c3 is equal to 5. Okay? So it's a system of equations, right? Because all these additions and scalar multiplications just take place component-wise. All right, but now we're back to just thinking, all right, what I'm really trying to do is deal with this augmented matrix, right? 1, 2, minus 1, 2, 4, minus 2, minus 1, minus 1, 3, augment negative 1, 4, 5. Okay, so it's equivalent to solving that. And so now, what do I need to do with that? Well, if I do row reduction, and I won't show you the details now, but I encourage you to work them out at home. If you row redo this, you get 1, 2, 0, 0, 0, 0, 1, 6, 0, 0, 0, 1. Okay, so what does that mean? Well, remember, you've got a bunch of zeros here equal a non-zero thing here. So this is reduced to the equation 0 equals 1, which has no solution. So that means there is no solution. The system is inconsistent. And what that means, going back to the original example, is that there's no way to write this vector as a linear combination of these three vectors. In fact, if you look at it, if you look carefully, you might notice that a relationship between these first two vectors, this vector times 2 is equal to that vector. So when you multiply one vector times the other, you're actually, when you multiply this vector times 2, when you add any multiple of this vector to any multiple of that vector, you just get a multiple of the original vector. So these two vectors together aren't really giving you anything new when you take linear combinations. Having one or the other of them and eliminating one of them, you would still get the same set of linear combinations that you get with both of them. So that's an idea that we'll try to make more precise later on. Okay, so we want to make, we need another name for this notion of the set of all possible linear combinations you can make with a set of vectors. So we'll call that the span. Seems natural enough. So if I have a set of vectors v sub I, then the span is just the set of all linear combinations I can make with those. So suppose that my set of vectors is v1 through vp, then putting any coefficients in front, c1, v1 through cp, vp, the ci's can be any scalars. So if you go back and, let's take a look at some simple examples. So the span of the 0 vector is always just the 0 vector itself. So there's not much you can do with that. So the span of this guy is just, so the span of a set of vectors will always be a set of vectors. So that's just the 0 vector. Now the span of 1, 3, well, what can you do? You only have one vector, so all you can do is multiply it by any scalar you want. So you should think of the span of 1, 3 as really representing, in some sense, just a line. So if you have 0, and this represented the vector 1, 3, then the line of all possibilities through 1, 3, that's the span of 1, 3. Now if I have the span of 1, 3, and 2, 1, well then you should go back and look at the picture from the earlier slide. So let's take a look at that. Right? So this, the span of 1, 3, which is actually red, and the green vector is everything in R2, right? Because we can get any point in R2 by making some linear combination going this way and that way. Just like, you can write any point in the plane as some multiple of 1, 0, and 0, 1. This is just a different way of doing it. So now back over here on span. So we know what the span of these two guys look like. This is all of R2. Okay. This is just a line in R1. Now here, what's going on here? Well, notice that these two vectors are the same as these two vectors, except I've tacked on a 0. So they're in R3, but you're never going to be able to get, if you take any multiple of this, you'll still have a 0 coordinate here. If you take any multiple of this, you'll still have a 0 coordinate here. So no matter what linear combination you take of these guys, you'll still have 0 in the bottom. So what that means is that the z coordinate is always 0, and what you're really just getting is, I guess I would call this the xy plane in R3. Okay, everything whose z coordinate is 0. Now over here, if I take the span of 1, 3, and 2, 6, I have two vectors, so you might say, well, I should get R2. But be careful, right? Because 1, 3, and 2, 6, one is a scalar multiple of the other. So the fact that I have 2, 6 is twice 1, 3. That means that if I add any multiple of 1, 3 to any multiple of 2, 6, I still get a multiple of 1, 3 itself, right? Because so if I had something like C1 times 1, 3, maybe I should write it over here. So C1 times 1, 3 plus C2 times 2, 6, what is that? Well, this is just 2 times 1, 3, so this is just C1 plus 2C2 times 1, 3. Okay? So anything that we can write as a linear combination of these two guys, we can write as just a scalar multiple of 1, 3. So again, it'll just be this line going through the point 1, 3 in the plane. All right, and so finally, the most complicated one is a guy like this, right, where you've got three different vectors in three-dimensional space. And you think, okay, well, so maybe generically, the span of that would be three-dimensional. But you have to, if you look a little more carefully, you'll notice a relationship between these three vectors. What is it? Well, 1 plus 2 is 3, negative 2 plus 1 is negative 1, and 4 plus minus 3 is 1. Right? So what that means is that this vector plus this vector equals this vector. So if I have any linear combination, and so let me just call these vectors for now, I'll label them down here, v1, v2, and v3, right? So what's going to happen? Well, c1v1 plus c2v2 plus c3v3, since v3 is v1 plus v2, this is equal to c1v1 plus c2v2 plus c3 times v1 plus v2. Okay? So what's that? Well, that means it's c1 plus c3, and maybe I should remind you that these are all vectors that I'm talking about here. Keep my vectors and scalars separate. So this is just c1 plus c3 times v1. That's the coefficient of v1. And what's the coefficient of v2? Well, it's c2 plus c3 times v2. Okay? So anything that I can write as a linear combination of these three vectors, I can write as a linear combination of just the first two vectors. So that means that the span of these guys is actually equal to the span of just v1 and v2, and that means that it's at most two-dimensional. So these three vectors, if you look at all linear combinations of them, instead of somehow filling out all of three-dimensional space, their span is really just a plane in a two-dimensional plane in R3. So generalizing these notions are the things that we're going to talk about in the upcoming weeks. And that's it for video lecture 5. Thank you for your attention.